so let's get started. We're actually not going to start with this. This is the main unit. We're actually going to start with this guy right here. So this is the back plate. This is what you install on the wall, and your wires from your compressor. I'm not, air conditioning guy, so I don't know what the official term is. But the big box in the attic, the wires come from here and they hook up to here, and it's going to take this off so we can see the insides. Interestingly enough, one of the things that the thermostat does not need is a battery. It has a battery within itself, and it charges. Now, the one thing I did learn about air conditioning systems, I guess, is that there's different kinds. First of all, as you can see, I only use about 4 of these. I think it's these 4 right here. No, these 4 right here. And traditionally, they make thermostats that don't have batteries. And the way it works is, it has to be compatible, but a circuit is completed, and your device draws power from that. The problem is that, for example, mine's a good example of this. Mine does not complete that circuit. In fact, this is not correct the way it's laid out, but essentially one live wire comes in, and I have 3 different wires. So I have a total of 4 wires in my system. And the hot wire comes in, and then these 4 essentially will close a relay. One is for the, let's see if I can get this right. Probably won't. One is for the fan, one is for the heating system, and one is for the air conditioning system. So 3 different things, one live wire. How can the system charge without making a connection? And this is real interesting, and I found this out on the forums. Some guy was posting that his water heater was making a weird sound. Turns out that the way the Nest system charges itself, it essentially turns on the heater on and off really, really quickly. And it does this to draw, very, very small amounts of power to charge itself. And this was confirmed through the rep, I guess, he spoke with. And it makes sense. The cooling and fan side, I guess, are more reactive, because as soon as that works, it clicks and you can hear it. And the heating system might be less reactive. But in his sense, I guess the heating system he has was very reactive very quickly. So you can actually hear his heater turn on and off really, really quick if you listen to it. So that was interesting. And as in hardware, we have a couple passives and some interesting things right here. This is really small, so for me to get part numbers on here was really, really hard. I'm going to link to the teardown, so they have a bunch of good stuff on there. But I'll tell you some of the main points, at least on this board. We're actually going to call this the back plate. And the reason I'm going to call it the back plate is because the firmware calls it that. So this is the back plate. And when I say firmware calls it this is actually running its own firmware. And we'll see that in a little bit when we take apart the firmware. This is an ARM M3, I believe, made by STM. And the cool thing about this is that it runs independent of the main processor. Think of this as a co-processor. And it runs, and I'm assuming they would need this for that power management system I just described. Because, if you just think about this, these are just wires, switches, right? They're closing. And to manage that and to draw power efficiently, remember, it's charging itself off the closing of a really fast switch. Sorry, I messed up the camera. But I'm assuming this is why this is there. Again, I don't know, because this firmware is actually hit inside of the main application firmware. And again, this will make more sense when we get to that. But so yeah, this is an independent coprocessor right here. And then we have, I think this is a temperature and humidity sensor right here. I don't know how well you can see that. Maybe. Okay. And then I believe this is like a multiplexer. The teardown has it. This is a multiplexer, and then you have a whole bunch of other ICs. But that's the only interesting part about this back plate, the fact that it runs its own separate firmware, and it's independent. It's actually not really a coprocessor if it has its own firmware and it's running. So, and the way this works is this connects right here. So these 2 devices connect like this. So yeah, that's it. And really cool note is that this has a low level here. I took it out, but so when you install it, I mean, the way they make it is you really don't need to be an expert in the air conditioning system. It's quite neat. It comes with everything included. Even the tools will take it apart. So that's that. I don't think I have any other notes on this. All right, guys. We're going to move on to the display board, and that's what we're going to call this, the display board. And the one thing I want to do is I want to apologize for the crappy camera I have. I'm sorry I don't have a legitimate setup, at least not now. The second thing I wanted to mention is why I'm wearing these gloves. And it's not just because I wear gloves when I tear down things. It is because this sort of, I don't know how well you can see this, but it's like a greasy, it's oil to, when this thing spins, because the way you navigate the menus is this outer casing spins. And that's how you navigate the thermostat. And it's all in there, and it's also around this rim. So that stuff gets really annoying after a while. So yeah, and like I said, I have a link to the teardown, much better teardown down below. So I won't go over how disassemble this. So here we have the battery, and I'll take that out. And I'll show you some things. And I'm actually not going to take the shielding out. I have another board I want to show you that already has it removed. I just want to go over some things and show you how it's laid out inside of this enclosure. This really is our only attack surface. And if you can't see what this is, it is a USB micro. And when you talk about attack surfaces, how can we interact with this device? Well, all its ports are closed, so you can't, when you port scan it, it shows nothing. And even your phone doesn't talk directly to this device. It talks to the Nest Cloud, and the cloud talks back down to this. So when it makes sense for Web API, because the web is what controls this. And when we talk about taking it apart and finding out exploits, this is really our only entrance into the device. And it's actually a pretty good entrance, which we'll go over. Here we have, this is just shielding. There's actually nothing underneath here. Here we have the motion sensors, and there's two of them, and they're very interesting. Well, I'll turn it around, you can see this. And this is sort of like an optical scanning device that senses this ring moving, and it determines which way to move the cursor. So let me go ahead and get a one that doesn't have this shielding. This back. All right, guys, I had to adjust my my camera because the autofocus feature, I guess, wasn't working correctly. So I apologize for that. Hopefully it'll be better. The only bad thing now is that I can't really move because it will be out of focus. So this is that board that we saw back inside of that enclosure. And I wanted to show you, essentially this just went to the display. It was a flat flex cable that went to the display, which I can probably show you. Not that much, not that very interesting. Here's that cable right there. And then right here, we had these two guys. Like this, and another one right here. And this is that optical scanner that scans that outer enclosure, determines whether you're moving up or down. And this doesn't have any connections, and in fact uses the 4 screws to make a connection. This is the optical, the motion sensors. One is near field, and one has the other one has a really wide viewing angle that determines, the first one, the one that's near field, will determine whether you walk up to the device. Look at that right there. And that's really nice because when you walk up to it, it lights up, it illuminates, and allows you to adjust it. This is sort of that sleep management system. And if you go to one of the technical menus, you can actually see it'll show 1 if you're right in front of it, and if you stand off to the side, it'll actually be 0, and it will eventually dim. And then the other one is, like I said, a very wide viewing angle, and that determines whether the auto wave functions. So if you're not home after, let's say, 4 hours, it will determine that you're not home, and they will turn off the. You can actually set this, but it can turn itself off to save you even more money. And that's really, kind of cool, I guess, but it can be dangerous because if someone has access to this schedule, they know whether you're home or not. So that's that shit. Now we have this. This is the back of it, or this is what we saw in the last video. One of the first things you're going to notice is these guys right here. This is the, initially you think, hey, exposed pads, which are very different from these exposed pads, and you think this is interesting. And in fact, these, all of them, map directly to the Zigbee chips, 2 of them. And again, this is more of that suspicion as to why dedicate these chips, these pads to the Zigbee if you're not doing something with them, right? You have to be doing something. And why put them? What's the point? It could have been made for like some sort of FCC testing, but then you don't have the Wi-Fi ones as easy accessible as the Zigbee ones. So the tinning is me because I soldered wires to them, and I put a logic analyzer in. There was initialization, but that's about it. So again, interesting that they put this here. Over here we have, again, the USB, but without getting too ahead of myself, this right here. You can hardly see it, and maybe in another video, I'm sorry, in another, when I can get you closer to this, is you'll see that these are, I think, 16 positions, and these are very fine. I think close to 0.5 millimeter pitch between each contact, and this is where you're gonna have access, serial access, JTAG, and then some very interesting pins right in the middle, which again, we'll go over. But again, when I took this apart, one of the first things I did was, hey, these are interesting. Nothing, dead end. So we're gonna go ahead and flip it over and we'll take a look at the front of it. All right guys, I did some adjustments there. It might have been the light, but we'll see how it goes. So this is the front of the board that faces the LCD screen. Before you go and say that Nest does a crappy soldering job, this is actually not on there anymore. These were taken off, and I'll explain that in a little bit, but let me go and give you an overview of what all the chips are. You have the main application processor, A3703. And then you have RAM, flash, 2 gigabytes by the way, which is quite a lot if you think about this. And then you have Wi-Fi right here, USB and power management, which again, we'll look deeper into that in a little bit. And then in this corner, if you flip it over, this is actually where the battery connects to the board, so I would assume this is all power stuff. And then right here, these QFNs are the Zigbee part of the circuitry. This is the Zigbee SoC, and this is the front end. And again, those back exposed pads map directly to this chip actually. So one of the things early on, and the reason why the chips come off, is because those pads you saw in the back, there's a lot of them, as you can see. And without knowing what I'm really looking for, it kind of makes it burdensome going through all of them. So by taking these off, it makes things a little bit easier. The problem is that this stuff, if you look at the teardown, you'll see there's an underfill. Now this is different than just potting. In fact, you can kind of see here. You see the black ring around this, but it's not on top of this. And this is a little bit different because when you have it on top, sometimes you can heat it up and it'll chip away. But underfill actually goes underneath the chip. And again, it's the same thing. It's a conformal coating for moisture and vibrations, but it makes it a real pain to take these chips off. And the ones that had it were these right here. The RAM, the application, pretty much all of them except the Wi-Fi and the Zigbee. These didn't. These are actually quite simple to get off. So I'll take those out. But these again had that horrible underfill, and I did an okay job for what I had. And then this one came out. And this one was probably one of the harder ones because you have such a large space. And the good thing is a lot of the underfill you can, I guess on the sides, you can use different types of I forgot what it's called, but essentially acidic compounds to etch away on the sides. And sometimes, like for example, right here, you'll be able to see in the video, there's actually exposed pads here. So you can kind of see them right there. 4 of them, really, really small. But again, this was all covered with that underfill gunk. So getting that stuff off of there was key. And not only seeing this, but eventually lifting the chips off. Also, some weird things on this board is in the fit of rage I had applying heat to this. Some of these other chips floated off, but as you can see, this right here and this right here and these two. So these 6 pads were exposed. There wasn't anything here. And again, oddity, because I don't know what they were for. There might have been some sort of tuning to tune the microcontroller with a different crystal. Maybe, I don't really know, but again, I just wanted to point that out. There were 6 of them, here, here, and here. So that's it. Again, I gave you a little bit more than what I knew when I started out, because obviously when you start out, you just don't want to go ahead and rip these chips out, because there's no way I'm going to put this back on there. So this happened after what we're going to next, which is the firmware. After that, I came back and I knew how to get these off just to find out where some good pads were. So that's pretty much it for the front. All right, we're going to do a very brief overview of the firmware, at least initially, because that's how it happened. I didn't spend much time looking at this because static analysis is great, but I'd rather see it running and interact with it. So yeah, I don't spend much time with it. I just wanted to look at it, and I'm going to show it to you the way I saw it initially, at least. The first thing I want to get over is, how does it even update? Well, it normally does it, ideally over the air and automatically. So there is no user intervention. There's no check for updates. Nest at some arbitrary time decides to publish their update, and then the thermostat will check periodically for a new update, and then it will go and download the file and update. Now, in the event that process does not work, there has to be a backup plan, right? That's where that USB connection comes in. When you plug the device into a computer, it mounts itself like a mass storage device, like a thumb drive. And you drop this gzip file onto it, and then this is very key here, it does not update until you put it back into the device. I'm sorry, into the back plate. So what happens is you mount it, the device recognizes that it's mounted, you unplug it. And this is gets really interesting, because when you unplug it, it says plug it back into the base to finish the update. So it now knows that something's happened. It has to have already unpacked the gzip file and know that it's an update. It just needs to finish, and in order to finish, you have to plug it back into the base. So that's very key to understand, especially when you talk about things like time of check and time of use. You want to keep track of what's actually going on. Is when you first put the device in there, does it just store the gzip file, or does it unpack it, read it, and then when you put it back into the base station, does it actually run? And that's actually how it works. So it's something very key that I learned, and that actually happened after I did the static analysis, a deeper analysis of the firmware. So, and by the way, you can get this sniffing your network for this, the URL, or you can probably just do some good Googling and find it. And J49 is the second, so this is the second generation thermostat, and J49 is the code name for it. The other one you might see is display, or diamond board, and that is for the first generation. So you're looking for J49. And here is some stuff. I'm going to ignore this. This does not exist right now because I ignored it. I saw this P list. I knew what it was. It was essentially it's a manifest. It's everything that's inside of here. Ignore this. What is that? Doesn't matter. This is actually very key, and we'll see that later. But this describes the contents of this. So I don't think there's anything really good in here. And yeah, I forgot. It won't. You can't read it correctly. So we'll go to contents. Triggers is just pre and post scripts that it runs, and it has to do with logging and keeping history of it, and it clears itself. Not very interesting. Installations though. This is where earlier I mentioned that the backplate runs its own firmware. Where is this firmware? It is in program. BP backplate. And this plist file, which we'll open, is actually, if we can see this full screen, it's actually this data is the firmware itself. So this is a microcontroller, it's an M3, so it's not as interesting as the application processor, which is running Linux. This is going to be like a super loop. I mean, you could chop this up and look at it yourself, but it was just interesting that that's the way they did it. It's a plist file that after the board decides to update itself, it will actually has another application that updates the backplate, and it uses this to do that. So we'll get out of here. Okay, so in image, you have the root file system, and I'll give you a quick look at it. Maybe not. Where is this? There it is, but again, we're not going to look at it right now, at least because I kind of just did that. I kind of opened it, glanced at it, and said, okay, I'll get back to that later. So like this. Okay, so I went over program, which is the backplate, root file system. Stream are going to be your two early on components, which is your SPL, second program loader, and this is U-boot. The first bootloader is going to be the Texas Instruments X loader, And then after that, it boots U-boot, which has a directive for the kernel, which is here, and the root file system. So here's our kernel. Here is, this is not there normally. I did this, but here's your U-boot image. And again, I did not do that initially. I did that after I needed to, which is, I'll show you why I needed to look at this. But yeah, that's it. So now I'm going to, after this step, what I would want to do is find some stereo access on the device. How do I do that? Well, let's go and look at the board. That'd probably be a better way for me to show you that. So let's go look at the board. All right. So one of the things I've been stressing about is getting some sort of show access to the device. Why is that important? Well, if you think about it, there's things that we cannot access just with the firmware image. Things like any sort of memory dump if it crashes. Those additional mount points, we can't access them from a firmware. They're on the flash device. We could read the flash and then sort of try to mount it and see if that leads anywhere. But the problem was, at least with this, is I could not take the piece of flash out and then put it back in, obviously. Not with that underfill. And those points I did not see until after I started taking out the underfill. And by that time, I decided that I was going to destroy the board. So at that point, you just keep on going in. But I'm getting ahead of myself. Why did I take these chips out? Well, this is a lot of work right here. And all these pads, testing them out and finding out what they go to is really, really hard. Especially considering that these pads actually, at least the gold ones, have a sort of thin film on top of them that makes it a little bit difficult to get a read on. So what I did focus on was these pads, of course, which I already knew were dead end, and then these USB pads. Let's see how close we can get to that. I don't know how I'll zoom in. There it goes. So there's actually 14 positions, and then the two outer ones make 16. And like I said, 0.5 millimeter pitch. And I actually tried them. I wasn't getting anything. But what you will soon see is why I wasn't getting anything. And that's important to the progression of this project. So once we get the chips out, what's next? Well, it's pretty intuitive. We have a data sheet and we just work backwards. So we know what we're looking for. We put our meter in a continuity test and we put one end on this side and then just find out where it goes on this side. So after doing that, we get something like this. Now this looks like a whole bunch of mess. And what it really is just a blown up picture of this side of the board and me taking different sorts of measurements. You can find a lot of neat stuff just with the multimeter. Things like resistance to ground is very important, especially a lot of times the data sheets will define what the pull down resistance should be. So like I said, measuring as much as you can is really important. So with that being said, what we find out is that on here, I don't know how well you can see, probably can. And again, don't worry about this junk. This is just my notes, and it probably won't make any sense. The important thing is that there actually was serial access here at this point. In fact, pin 4 and 5 are transmit and receive. Now, why didn't I see anything? And I'm actually going to tell you what the rest of the pins are, but why didn't I see anything when I was using my logic analyzer? That's because when the device boots up, this is what you see. And this is something that I should show you on my computer, but I'm not because, well, for one, the voltage level that this operates at is 1.8. And in order for me to show you on a terminal, I would have to build a little logic conversion circuit, and I'm not going to do that. Instead, what I'm going to do is I'm going to bring out a nest that I've already modified and have taps for, and we'll hook it up to my oscilloscope and we'll see the output. But first, this was the output. Once I confirmed that this was transmit and receive, I built that circuit, I hooked it up to my computer, and here you can kind of read what I got. So anyone who's messed with U-boot or any embedded system knows what's missing is, just empty space. Ideally, what I would want to see is some U-boot debug output, and then the kernel debug output. The problem was I wasn't getting that. Not just was I not getting that, I wasn't allowed to break the sequence. So one thing with U-boot is that you can pause the sequence, the boot sequence, sort of like BIOS, and you can modify the environment variables and tell it to boot differently. I couldn't even do that. So I suspected that U-boot had been built in a certain way, and that was confirmed. Where I'm actually going to show you that. We're going to go back to the firmware. So after I saw this, I knew that it wasn't going to be as simple as I thought, and I needed to go back and understand how U-boot was built before I even started working on the kernel. Because at this point, I don't even know if a shell is spawned at boot. I don't know if, how is a serial output mapped. I don't know anything because I don't have U-boot here in U-boot there's a directive that silences the kernel. So we need to start from the beginning, and that's U-boot. So I'm actually going to take you back to the firmware image, and we're going to look at U-boot one more time. All right, so U-boot wasn't being friendly with us, so we need to understand what was making U-boot bad. So we can go to, put this right here, and then put this, fit this in here. We'll start with U-boot. So contents, relations, streams, PL. So we string it out. Oh, I forgot, it doesn't like it. We can see that this silent equals 1. So when you compile U-boot, you can compile it in such a way that when you add this directive, it will suppress its own output. That, coupled with this boot delay equals 0, is what gives us the issue with not being able to stop it and modify it. If these things weren't here, we can actually stop U-boot from starting, modify the arguments that are passed with the kernel, and make some kernel messages come up. But I can't do any of that. But interestingly enough, we actually see the quiet statement here. And then this is good news, but again, because of this quiet statement, it doesn't matter. At the end of the day, the purpose of U-boot is to load an entry point and then tell the system to never come back. And it can mount other file systems, and it can choose between which one, if it can boot over a network. And that's really important because you can boot, see this MMC boot and NAND boot. This will actually be pretty important because what's going to happen is I'm eventually going to map the rest of those pins, and one of those pins is going to be a boot selection pin, and we'll see that in a little bit. But in order for, I didn't know any of that at this point. What I knew was that the update process, well, I'm sorry, I skipped a whole bunch of stuff. I patched U-boot. After patching U-boot and fixing those directives that I didn't like, I recompiled, I put the firmware back together, and I put it back on the nest. The problem was that I got about halfway and decided, hey, I'm going to stop. I'm going to restart. And it did that. It restarted, and it did not update. So what that meant is this signature file that I ignored was being enforced. It wasn't just there for decoration. And this is, at this point, I needed to go back to the root file system and understand what was going on. So we go back to the root file system. We go to this directory, and we find out what's going on here, right? Because this is going to be the app that's running 90% of the time. This is what gives you your interface, and this is your app that controls everything pretty much. And at some point it breaks its sequence and calls out certain routines to start the update process. Not just the application processor's update process, but the backplate processor's update process. So this NLBP, that's Nest Labs backplate updater, and this is in charge of parsing the file out and that plist file out and updating the backplate firmware. Again, this is all part of a sequence, and what I want to stress out is that it's getting halfway. So what that means is that certain things are being executed and ran, and at some point one of these checks fails, and it might not be a check. It could be, well, it's going to be a check, but what we want to do is kind of tweak things around, find out what's causing it to fail. What I do want to show you is the script right So for example, at some point this gets called, and here it evaluates whether this is valid, and this binary OSM is in charge of, well, we're passing it a root certificate and other, good stuff, and it evaluates it, and that's where I suspect it's failing. But again, without having some sort of dynamic analysis of it running, I don't know for sure. I need some debug output. Interestingly enough, this Dropbox script, another thing I wanted to show, was this thing is related to the USB mass storage device. So this is in charge of providing the backing for that. What that means is there's no, it doesn't have a thumb drive within itself. What it does is it emulates that. And in order to emulate it, it needs, for example, how much space do I give? Things like that. And what's a state table look like? And this is what, it gives you all that information here. And this is interesting because if you keep your options open, and if for some reason something doesn't work out, you know that this is an avenue to explore. But at this point, what I started doing, and to understand this script and understand where I was messing up, you start doing simple things like, for example, let's not modify or patch anything. Let's just add a letter to here, and then gzip it up. How far does it get that time? Well, you know what? Let's just add a appended letter to the already gzip file. What does it do then? And you keep on doing this, minor changes, understanding it, because pretty much the only debug messages we're getting is that loading bar. We don't know what inside of it, what's going on. And again, this is critical to analyzing these binaries. Adding more characters, removing characters, and maybe let's get rid of this plist file. What happens? And we can keep on going back and forth, back and forth. I wasn't going anywhere. In fact, what was going on is I was kind of getting frustrated with it. So we're actually going to go back to the board, find out what those other pins are, and see if there's anything interesting there. And turns out there was. So we'll go back to the board now. All right. So back to this drawing, and this is not going to be some sort of reference kind of material we can go back in. This is kind of just giving you some sort of overview of some information, because this is not a good way to represent what I'm trying to portray. You can't really see any of this stuff really well. But I finished mapping these pins out, and we found JTAG. We found, very interesting, I found that pin 3 was a part of a power rail. Which I didn't understand why at first. Why put a tap here for power? It didn't make any sense. Well, pin 6 was labeled sysboot 5 from the application processor. And looking at the data sheet, there is 5 pins on the application processor. Whether they're pulled high or low will determine a certain boot order. It's a little bit more complex than that. There's actually a software-defined boot order as well, but like I said, it's both a hardware-defined boot order and a software-defined boot order. But the data sheet will let you know how that works. So and actually, we're gonna look at the boot order right now. Let me show you what I mean. So here, and again, this is not reference material. I'd recommend you pull up the data sheet and look at it yourself. But let me show you this. This is a state table of how the device boots. The boot sequence. And what I mean by software-defined booting and hardware-defined booting is that depending on, first of all, if it's a warm reset or a hard reset, if the processor stays on, there's different ways it can boot. And like I said, this is the state table that I referenced to determine where it's at or how that sysboot plays into effect. So again, I recommend you pull up the data sheet and look into that. But assuming that it is at a hardware-defined boot, the boot order is defined by hardware. There are essentially 5 pins that either get pulled high or low, and how they are pulled determines how the device boots. So, for example, in this mode right here, if these pins are pulled in that sequence, it will boot first USB, then UART3, then MMC, and then the rest. And this was key because there's 2 major, you can't see it, but there's 2 major groups of these boot sequences. Pin 5 determines that. So what pin 5 does, if it's low, it is a memory preferred booting order, and there's more to this. You can't really see. Sorry. There's more to these, but so pin 5 being pulled low, which it is by default, is memory preferred booting order. Now, remember that power row I was discussing? Well, if we pull pin 5 high, it now goes into a peripheral preferred booting order. And this was really important because it completely changes the way it turns on. The problem is that POR, power on reset. There's also a determination of a warm reset. A warm reset and a power on reset are two different things. And we actually see that. And actually, I'm going to stop at this point because one, the video is getting a little bit long, and I want to actually show you what happens when I pull that pin high, with a real demo. So the important thing is that we need to initiate a power on reset, not a warm reset. And you're going to see that now in a little bit, but the difference being is that with a power on reset, the device turns off. Warm reset, it doesn't. And how do we turn on the device if we don't have any buttons? Well, when I was mapping out the pins, there's one pin I have yet to find, and that is pin 2. Now, pin 2 is right next to the power up. Pin 2 does not map to any pin on the application processor. So this could be a reset pin. Now, the application processor does have a reset pin, but it's a complex power on sequence, and I don't expect it to tie directly to some sort of ground or power rail. What more than likely, that USB power management chip that I was discussing earlier, it is in charge of initializing the device and turning it off. And this is actually was confirmed because when you plug it in USB to your computer and restart the device, it actually modifies the boot order itself as well. So there's two ways to modify the boot order. You can modify it by pulling these pins high, sysboot 5, which is pin 6 on that USB header, or you plug it in USB to your computer. It actually modifies the boot order. So pin 2 could be our hardware reset, or I'm sorry, power on reset that we're looking for. What I imagined is that they had this entire a cable going from here to some sort of like another breakout board where they had like a reset button. They can do that because there is no way to reset this device. The only way to turn it off is to hold it, but that does a warm reset. It does not do a power on reset. So the next thing I'm going to show you is I'm going to show you what happens when I pull that pin high. But last note, because that's actually going to be the last thing I show you, is me pulling that pin high and it changing the boot sequence. We're going to see some cool stuff. But some other notes that some hints as to where I'm going with this is this. Let me bring up the chip, the board. I'm sorry. So there's USB. This is USB and power because it has to charge the battery. It can charge via USB. The interesting thing about this, so at one point I messed with it and my button broke. Now when I say button, I mean the device turns like this, and you can also click it like the display. That button broke. It wasn't registering that click. So at this point I had known a lot about the device, and I debugged it. What I mean by debugged is you can find the points on the pads where it pulls it to ground, and I verified that it was pulling to ground. So it wasn't a hardware issue like the button broke. It was a software issue. I didn't know how to fix it though. And this was again one of those like weird luck moments where I decided to buy a USB on the go cable because this USB IC works with USB on the go. And all I did while the device was on, I plugged in a USB on the go cable, plugged in a thumb drive, and it re-enabled the button to work. And it was just shocking because I didn't restart it. I didn't do anything. And prior to this, I had done so many different things. I had put in old firmware, put a new firmware. I had taken out the battery, put the battery back in. I had done so many things. And all it took was me putting a USB on the go cable, which, by the way, is a separate cable. It's not just a USB cable. The way USB on the go works, it has an ID pin that determines that, hey, I'm a host now, so mount the device. Because normally this operates as a target device and not a host. So USB on the go will put it into host mode, and it must have done something because the click button worked again. So that's really interesting. But again, what I'm going to do is get a modified nest that I have that I've been using, and show it to you on a logic analyzer. So give me a second. All right, so here's this modified nest that I have, and what I did, there was no way I was going to solder to this. I mean, this is ridiculously small. This is a blown up image, and look at it, my finger's barely the size of this. So there's no way I was going to solder directly onto this, and I couldn't etch any. This is a multi-layer board, a very dense multi-layer board, and I couldn't find traces that I could etch them out. So what I did is I found pads, and the way this works is I found some pads, I labeled them, and then I soldered wire to them, and then I taped it down so that way it doesn't pull it off. And so the point is that this stuff is very sensitive. I mean, this is wrapping wire right here. It's so hard to see, and it's color coded sort of, so I can know what's going on. And like I said, it comes out through this. So the problem is that I only brought out, I didn't bring out pin 2, so I have to disassemble this, and this is kind of what's been prohibiting me from going any further, is taking this thing apart and possibly undoing those solder joints. So the only pins I brought out, and you can't see it here, but this is actually labeled. So starting from this side, it's transmit, receive. The third pin, the pin in the middle, is the sys boot pin. The pin next to that is a power rail, and then the last pin is ground. So what I'm going to do is I'm going to pull sys boot to the power rail. So jump that. And now I'm going to hook up my logic analyzer and show you my screen. What I'm going to do is I'm going to tap this transmit pin, and we're going to observe it. And you're going to see that we're in right here. You go from the X loader to U-boot. You're going to see some stuff, and you're going to see it change because I've jumped it right here. So let me go ahead and hook up my logic analyzer, and I'll show you that. I was going to use an oscilloscope, but I remember that the logic analyzer is a lot easier to see, so we're going to use that method. All right, so here we have the logic analyzer hooked up, and I've already configured it. It's going to trigger on the rise, so when it turns on, because I'm going to turn it off right now, and then it's set up serial, so channel 0, only one I'm sniffing is transmit. So I'm going to go ahead and start it, and then I'm going to reboot the device. And this is a soft reset, or a warm reset, I'm sorry. Okay. Now, here we go. Also, sometimes, just future reference, the distance matters, so you can kind of guesstimate what's happening here if it's looking for the boot order, or if it's doing other stuff behind the scenes. But take a look. So after that X loader happens, and this is what I mean by warm reset. This is not a hard reset, so it's not doing ideally what I would like it to do, which either boot UART or through USB. But what's happening, it does change it in a very slight way. So we see Texas Instrument X loader like we saw earlier, but then we see this right here, MMC multimedia card initialization failed twice, and this gets, because part of that state table determines that it will try the device a certain amount of times before it moves on to the next one. So you can see that this was not there before, but by jumping it, sysboot pulling it high, which should put it in a peripheral preferred booting order, although well, actually no, I guess I don't think MMC qualifies as peripheral according to the state table, but yeah, USB and UART are, MMC still counts as memory. So even though we're pulling it high, it's still, like I said, pulling, all we're seeing is MMC initialization failed. But again, this just proves that that sysboot pin does modify the boot order, as well as hooking up USB. So the next step will be to take the device apart again and look at the that pin 2. Find out where it goes to, see how it interacts with the USB IC, USB and power management IC, and then go from there. There is some more stuff, but this video is getting a little bit too long, and I'd rather save the other stuff for the next part. But yeah, that's pretty much it. And if you have any questions, feel free to either there's some contact information down below, or just leave a comment. And that's it.